In this video, we're going to talk about some of the practical details of preparing buffers and talk about how to prepare a buffer with the target pH by doing just a couple of very simple calculations. So, a buffer is a mixture of an acid, let's say a weak acid, and its conjugate base. And so the simplest way to prepare a buffer would be to start with the acid and conjugate base. Let's say both were solids, dissolve both in water in the appropriate molar ratio or ratio of concentrations, and there you have it. There's a buffer. However, for reasons that should become clear by the end of this video, we often prepare buffers using equal molar concentrations of the conjugate acid and base. We end up adjusting our concentrations later through the addition of strong acid or strong base, but we start with equal concentrations of HA and A-. The reason we do this is that a buffer works by reacting with added strong acid or strong base to neutralize a would-be change in pH. So, for example, the weak acid component of the buffer reacts irreversibly with any added hydroxide. Say we added a lot of hydroxide, much more than is present naturally in neutral water. These two are going to react irreversibly to form A- and water, and because hydroxide has been consumed and hasn't led to a change in pH, in fact we've generated water, the pH won't change very much. It'll only change to the extent that we change the ratio of HA to A- in accordance with the Henderson-hasselbalch equation. On the other side, if we were to add a large amount of strong acid to the buffer, that reacts with H3O plus to form HA and again water. And since this process is consuming that added H3O plus and converting it to water, on the whole, the pH of the solution doesn't change very much. All of that strong acid gets consumed, and the pH changes only to the extent that the A- to HA ratio changes. If we want the maximum capacity out of our buffer, then we need equal concentrations of HA and A-. That is the maximum capacity for resisting changes in pH due to both strong base and strong acid. Because when we start using different concentrations of the weak acid and its conjugate base, we lose the ability to resist changes either due to strong base or strong acid. We get the maximum bang for our buck when those two molar concentrations are equal, and it's important for an effective buffer to have approximately equal amounts of conjugate base and weak acid. A buffer that has a huge amount of one or the other stops really being a buffer as it loses the ability to resist changes in pH due to either strong acid or strong base. If we start with a buffer that has equal molar concentrations of the weak acid and its conjugate base, it's fairly easy to calculate the pH of that buffer by starting from the Henderson-hasselbalch equation. pH is equal to pKa plus the log of the ratio of the A- concentration to the HA concentration. When the two concentrations of conjugate base and weak acid are equal, of course this entire term divides out to 1, the logarithm of 1 is 0, and we can arrive at the conclusion that the pH of the buffer is equal to the pKa of the weak acid, of HA. This situation represents the center point of the pH range over which this system can serve as an effective buffer. And by adding strong acid or strong base to adjust this ratio above or below 1, we can alter the pH of the buffer. This can sometimes be practically more convenient than adding exactly the right amounts of acid and base to achieve a desired target pH. So how then do we go about choosing a buffer system to achieve a particular target pH? Well, step 1 is to choose HA and A-, choose the conjugate acid-base pair. It's important to do this such that the pKa of HA is within 1 pH unit of the target pH. The consequence of this is that the ratio of HA to A- concentrations should be between 1 to 10 and 10 to 1, and we can see that just by rearranging the Henderson-hasselbalch equation slightly to pH minus pKa equals the log of the conjugate base divided by the acid. You can see that if this difference on the left-hand side needs to be plus or minus 1 pH unit, that's going to constrain our ratio of A minus to HA somewhere between 0.1, or what we might call 1 to 10, and 10, which we might call 10 to 1. Step 2 of preparing the buffer is to use equal concentrations of acid and conjugate base so that we know the pH. When the concentration of HA is equal to the concentration of A minus, the pH is equal to the pKa. If we need to adjust that pH upward, in other words, if we need more base to increase this ratio A minus over HA, we can add strong base, which is essentially hydroxide, add strong base to increase the pH. Or if we need to decrease the pH, in other words, if we need to decrease this ratio by increasing the concentration of acid, decreasing the concentration of conjugate base, we can add strong acid, which is essentially hydronium H3O+, to decrease the pH. And importantly, we can use the Henderson-hasselbalch equation to figure out quantitatively exactly how much strong acid or strong base we need to add to achieve our desired ratio.